The 40% power tax. GPU interconnects now consume up to 40% of total system power just to move data across a single server rack. While flaps have increased by 3 orders of magnitude over the last decade, the energy efficiency of moving a bit over copper has hit a physical ceiling. We are currently spending nearly half of our energy budget on the tax of electron resistance rather than actual matrix multiplication. This thermal bottleneck is why training 100 trillion parameter models has become an infrastructure problem rather than a math problem. The parasitic capacitance of traditional copper traces effectively acts as a filter that kills signal integrity as we push toward 200 gigabits per lane. To keep scaling, we have to stop treating data movement as an electrical problem and start treating it as a wave physics problem. The escape bandwidth bottleneck. The primary limit for HBM4 and beyond is not the memory capacity itself, but the beachfront problem. We are physically running out of space on the edge of the compute die to place the pins required for electrical I/O. Silicon Photonics solves this by using wavelength division multiplexing to pack hundreds of independent data channels into a single optical fiber the size of a human hair. Instead of thousands of copper pins, we use a single photonic chiplet to move terabits per second. This shift reduces the energy per bit from picojoules to femtojoules. However, the industry is currently split on the laser source. While some labs are integrating the laser directly onto the silicon, others argue that thermal sensitivity makes external light sources the only viable path for production reliability. If the laser is on die, the heat from the GPU causes frequency drift, which effectively breaks the optical link. This mechanical reality is why the latest OCP standards are favoring remote light source modules over fully integrated designs. Architectural decoupling and thermal realities. Moving to optical I/O allows us to break the physical proximity requirement between compute and memory. In traditional architectures, HBM must be microns away from the logic to prevent signal decay, which creates a concentrated thermal hotspot that is nearly impossible to cool. Photonic interconnects allow memory to be placed meters away without a latency penalty. This enables a disaggregated memory pool where a cluster of GPUs shares a massive centralized reservoir of HBM. This sounds ideal, but the trade-off is the complexity of thermal tuning. Every micro-ring resonator on the chip must be precisely heated to a specific temperature to stay in sync with the laser wavelength. We are essentially trading a signal integrity problem for a precision thermal control problem. The May 2026 benchmarks for these optical fabrics show a 30% reduction in total training time for dense models, but only if the cooling system can maintain sub-degree precision across the entire photonic layer. The signal under the noise. The transition to photonic interconnects marks a fundamental shift from compute-limited scaling to fabric-limited scaling. By solving the beachfront problem and the energy wall in copper, we are moving toward a world where the entire data center operates as a single monolithic processor. The benchmarks from the most recent 2026 hardware cycles confirm that the performance gains in large-scale training now depend more on optical I/O efficiency than on raw TFLOPS. For builders and researchers, this means the bottleneck for the next generation of 100 trillion parameter models is no longer the size of the GPU, but the radius of the optical fabric. We are seeing a move away from the traditional discrete server model toward a unified compute memory mesh. The skeptics will point to the yield rates of silicon photonics as a barrier, and they are right. Current manufacturing yields for these optical chiplets are still 20% lower than standard CMOS. Watch the upcoming August 2026 production reports from the major foundries for yield improvements on integrated photonic layers. That number, more than any marketing claim about teraflops, will determine if the next scaling law holds. Subscribe for more.